10.3, we're going to take our correlation calculations one step further, and we're going to talk about regression. And what regression is, predicting a y when we know x. And so what we're going to do is we're going to come up with an equation for that linear relationship. Now let's do a little review from algebra. If you remember from your algebra studies, the slope-intercept form of the line is y equals mx plus b. The m, the number in front of our x variable, is the slope, and slope is always rise over run. It's change in y over change in x. And if you have a positive slope, it goes uphill. If you have a negative slope, it goes downhill. And then the constant that's added to that x term is the y-intercept. So it's the value of y when x is 0. Now in statistics we use the same idea, but our notation is a little bit different. So what we have is we have our y hat, which is our predicted y. Our b sub 0 is our y-intercept. So think of it, it's the value when x is 0. And then b sub 1 is our slope, and you can recognize that because that's always the coefficient of the term with the letter x in it. So this is an algebraic way to describe that linear relationship between two variables. Now, the regression line, or sometimes it's called the line of best fit or the line of least squares regression, is the equation that we're going to use for this. So remember, we have population parameters and we have our sample statistic. Our population y-intercept is going to be beta sub 0. Our sample statistic is b sub 0. Our slope of the regression equation for the population is beta sub 1. For the sample line is b sub 1. So y equals beta sub 0 plus beta sub 1 x. That is for our population, and then here is what we're going to use for our sample statistic. What has to happen? Same requirements as with correlation. We have to have paired data that come from simple random sample, has to be quantitative. The scatter plot has to show that it's approximately a straight line pattern, and any outliers need to be removed because they influence the mean, means they influence the standard score, and since when we calculate the R value by formula, that has standardized scores, so outliers are very influential. Now again, we're going to look at how we get this by hand, and then we will look at how we do it on StatCrunch. So b sub 1, remember, is our slope, and it's going to be r times the standard deviation of y over the standard deviation of x. Now, if you remember, the slope m equals the change in y over the change in x. Notice the slope of our line of least squares regression is our standard deviation of y over our standard deviation of x. It's also that ratio is going to be taken times r. So what happens here is our sine of r will always be the sine of our slope. So remember when we said r was positive, we had a positive relationship, we'll have a positive slope. Once you've calculated the slope, then you can calculate the y-intercept, and it will be the mean of y minus the slope times the mean of x. And we can do it by hand, or we are going to use the technology to calculate this. Now, how do we round it? Round it to 3 significant digits. If you're going to do it by hand, you only round at the end. If you, that's what this slide says. So let's go back to our example from the chapter problem, and we're going to try to predict man's height from the shoe print length. And so let's check. Is this a simple random sample? We assume that. We've already done the scatter plot, and it showed a roughly straight line pattern, and there were no outliers. So we are good to go, and we are going to use technology to find the equation of the regression line. Now here are some printouts from different kinds of software. The Minitab, they tell you your equation. StatDisk, they tell you that your y-intercept, and there's your slope, and you need to put it into the linear form. With TI-8384, they give you A is going to be the y-intercept, B is the slope. They give you those values. In SPSS, they give you the constant is your slope, and the y-intercept would be the shoe print. The same thing happens here with JMP. Let's go ahead and let's look at StatCrunch. So let's look at this, and on StatCrunch it's kind of nice because it is labeled in a nicer way, and here we have our intercept, here we have our slope, and so those are the two numbers you need in order to come up with a line of least squares regression. The other thing is right up here is height equals 125.40733 plus the slope of our line times the value for our shoe print. So it's got it both ways, pretty easy to find. Here we have our line of least squares regression. Our predicted y is 125 plus 1.73 times x. So let's think about what this tells us. This tells us if there's no length to the shoe print, our man will be 125 centimeters tall. Not going to happen. But for every 1 centimeter in length the shoe print is, the height, our predicted height, will increase by 1.73 centimeters. And so let's just go back and look at the formulas. We're going to get the same numbers, but I just want you to see how they work. So remember that R was 0.5912. Here we have our R, our standard deviation of Y, our standard deviation of X, and you can see we get the slope of the line. And then we're going to take, and this should have a line over it. Mean of y minus the slope times the mean of x, and we get 125, and that's what we got using technology. And then if we look at our graph with the line drawn in, you can see that the points are half are above, half are below. The distance above is about the same as the distance below. So it's a pretty good fit for a model. And we already used StatCrunch to find that. When we are going to predict, we want to make sure, first of all, that it really does fit the data pretty well. And then if we tested R and the R comes out to be statistically significant, then it's okay to go ahead and use that regression to actually predict. You don't want to go too much beyond the scope of the available data. That's called extrapolation, and it could cause some bad predictions, and we'll talk about that in a couple slides. Sometimes, if your R is not statistically significant, the regression equation doesn't make sense to use, then your best predicted value of the variable is its point estimate, which is the sample mean. Look at this graphic. We need to decide. And if the regression equation is not a good model, then you simply use the mean of the y as your best prediction. And if the regression is a good model, then you'll use your line of least squares regression. Now, let's go back and let's restate that. If it's not a good model, then your R was not statistically significant. If your R was statistically significant, so remember, we're going to use R to help us here. This tells us the same thing, but the thing that you want to remember, if your scatter plot is not a straight line, then do not use a line of least squares regression. We have a different model that fits better. Back to our product and average life expectancy. You've seen this data before, and we can calculate the line of least squares regression using the summary, and this is what we get. Now we'll get this same thing if we go ahead and we do it in with technology, and that's what I have on the next slide. This is using Excel, and again, here is my y-intercept, and here is my x variable. So basically, if we go back to our line, I'm going to go back a slide. If the country has no GDP, we would predict that the life expectancy is going to be a little more than 68 years. And life expectancy is going to go up 0.4 of a year for every, I think it was probably $1,000 of GDP. Now, things we know. Because we know the mean of x and mean of y, we know that the line will go through 21.52, which was the mean of x, and 77.54, which was the mean of y. We also know that the slope is positive because r was positive, and we know the y-intercept is 68.7. Since r was 0.809, we know r squared is 0.654, so about 65.4% of the variation in life expectancy can be explained by the relationship between life expectancy and GDP. That leaves about 35% that is unexplained. Now, in this case, only a third of it unexplained isn't too bad, because we all know there's a whole lot of stuff that goes into life expectancy. Here is our Archaeopteryx data, and again, we found this in the last section. Let's go ahead and go to StatCrunch, and let's So back to our Archaeopteryx data, you can see we have our line of least squares regression right here. We can also find those numbers. There's the number for our intercept. There's the number for our slope right there. And that's what we're going to use to predict. So we brought that text box over from StatCrunch and I put it in my equation. Now let's talk about what this means. This means that our arm length, because remember y was our humerus, x is our femur, so the humerus length would be a negative 3.65 if we had no length to our leg bones. That doesn't make sense, but it does give us something to start with. What it says, and this shouldn't be an equal, this should be a plus sign. So what this tells us is that for every unit length increase in the leg bone, the arm bone is going to increase by 1.2 units. That's what this means. Remember, our R was positive, so that means as the length of the leg bone goes up, the length of the arm bone goes up. So just remember, think about what these equations mean to us. Now let's talk about some of these lines. This is very important that you must have the explanatory variables and the response variables need to be established, because once you change them, your line changes. Okay, so this is predicting fat gain from the change in non-exercise activity. That's our solid line. If we flipped the x and y in our calculations, then notice the slope of the line is going to be different. They're going to cross, and right here where they cross is going to be mean of x, mean of y, but the lines are very different. So it's important that you establish which one you're going to use as your explanatory variable, which one you want to predict, which one you want to use to predict. Again, as I said before, the change in one standard deviation in x corresponds to r standard deviations in y. The line always goes through the mean of x, mean of y, and we've talked about when we talk about r squared, that tells us what part of the variation in y that is explained by the relationship with x. Now, they really do use this. This is an excerpt from a book written by Alexander Aston, who has done a lot of research into higher ed. But what I wanted to show you, these are the correlation coefficients between some variables. Now, we have between two variables, that's the first two, and then we have between more than two variables, which that's what is happening in the second. But look at what he says. Better than 2/3 of the variation in GRE performance can be explained in terms of SAT performance. So how did that happen? We took these correlation coefficients and squared them, and 0.85 squared is 0.722, which is more than 2/3, more than 67%. So these things really are used in research. We already talked about outliers a little bit in the last section, and now here we go. This is a graph, and we looked at the age that the first word was spoken in months, and this Gesell Adaptive Score is an IQ score for infants. So that's an IQ, and the mean IQ is 100, and the mean of X is going to be a little bit more than 10. And so you can see we've got some things happening. We've got child 18 out here that's very far from the clump, and then we have child 19 that's very far above. The red line is our line of least squares regression from all the data, but if we take out child 18, notice that the slope of our line gets a little less negative. And so from all the data, the amount of explained variation is 41%, but after we take child 18 out, it's only 11%. So beware of those outliers. Again, this only describes linear relationships. Both correlation and regression are affected by outliers, meaning they're non-resistant measures. You always want to plot before interpreting. We want to beware of extrapolation. That's when we predict outside of the range of X, and we've got an example here coming up in the next slides. Also, beware of lurking variables. If we were talking about, I want to predict someone's reading score from their shoe size, I'm going to find a strong correlation between reading score, and we'll just do the Iowa test, the Iowa assessment score on reading. I predict high reading levels when shoe sizes are larger. Well, part of that is there's lurking variables, and the lurking variable there is age. Bigger kids, older kids have bigger feet. Older kids usually read better than younger kids. So remember that even though we can predict, association does not imply causation. Okay, let's look at an extrapolation case. Okay, what we have is we have Sarah, and Sarah's height was measured in centimeters during her life between age 36 months and 60 months. So between the time she was 3 and 5. And we have that data recorded here. So what we want to do is we want to plot Sarah's height against her age, and we want to predict her age at 42 months. So here is the plot, and let's see, at 42 months I can eyeball it and say that I think she's going to be about 87 centimeters tall. I can also use my data to find my line of least squares regression. But what if I wanted to predict her height at 30 years, which is 360 months? What would that be? Well, let's go ahead. At age 42 months, her predicted height is 88 centimeters. That makes sense. But her height at age 30 years, using our line of least squares regression, comes out to be almost 210 centimeters. So that's going to be 6 foot 10.5 inches at age 30. How many 30-year-old women do you know that are 6 foot 10.5 inches tall? Think about, why couldn't we use that equation to predict Sarah's height? Well, we stopped collecting data when Sarah was 5 years old. So at age 30, 360 months is way out of the range of collected data, and this is what extrapolation is, going outside of your data. You're pretty darn safe if you stay within the minimum and maximum X values, but when you go outside of the data that's been collected, you want to be very, very cautious. Even strong correlations may not correspond to a real causal relationship. In fact, we already talked about that. If we did a study on shoe size and reading level, we're going to get a very high correlation coefficient. but we'd have a lurking variable. Now, in order to get evidence of causation, you have to have a properly conducted experiment. You also need to have a strong association, and that the association is always consistent in repeated trials and in varying conditions. That higher doses are associated with stronger responses, and that the alleged cause precedes the effect in time. You also have to think, is it plausible? Is it a reasonable explanation? If we look at smoking, how they went from smoking is associated with lung cancer to smoking causes lung cancer, all of these things happened. And they actually did have they put mice in cages and put cigarette smoke in the cages, made the mice smoke. The mice did not have cancer till after they had smoked. The more smoke in that they were exposed to, the higher their cancer rate, and it was a plausible explanation. Here's the deal with experiments: we control those lurking variables.